Okay, so this is the question. This is the January 2009 question 6B part 2. This is the circuit we're given. We've got a 25 ohm resistor, 400 ohm resistors in parallel. This is in series. The whole circuit obviously is in series, okay? And you have a parallel section and a singular series section with 25 ohms. The second part of the question says calculate the current going through the 25 ohm resistor. So you're trying to calculate the current going through this one. You've already calculated the current going through a single 400 ohm resistor, and you've done this by using power equals I squared times R. You know the power of the resistor in the question is 1 watt. 1 watt therefore equals I squared times the resistance, which is 400. So I equals the root of 1 divided by 400, and the answer you get is 0.05 amps. That's how much current is going through one of these 400 ohm resistors. We've got 0.05 here, and because this is the same resistor, this also has 0.05 amps going through it as well. Okay, so we know that. Now, going back to think about Kirchhoff's laws, to think about how current behaves in series and how current behaves in parallel, we need to use an example. So if we just keep that in mind, but forget that for a second. If we talk about a pathway, so if we had a pathway, for example, and there's 25 people walking along this path in the mountains, and suddenly the path splits, or the path forms a fork, if you like. Okay, I can't have 25 people walking down the right, and I can't have 25 people walking down the left. Why? Because before and after I must have the same number of people. If I have 25 people beforehand, I must have 25 people afterwards as well. So maybe if we just say about 13 people went down this way and 12 people went down this way. Okay? If we add these together, we still get 25. Okay? How people will actually move down the pathways depends on the resistance of the pathways. Okay, so you can think about a pathway that is really big, really wide, and one pathway which is really tiny and small and narrow. This has got high resistance. Okay, so we just give it an arrow, high resistance. This has got low resistance. Okay, if you have 10 people going down here, or if we can just say 10 amps worth of current going down a particular pathway, and this pathway splits into a junction, I'd expect, because this is low resistance, I'd think about 9 amps would go down here, and because this is high resistance, only about 1 amp is going to fit down there. But the point is, 9 plus 1 is 10. I've still got 10 amps of current after the junction, and I've got 10 amps of current before the junction. Okay, so in this question, we're looking at the current going through the 25 ohm resistor. So this is what we're looking at. Okay, you've just worked out that 0.05 amps of current goes down this pathway. So if we just think about the same thing again, so we've got one pathway here that splits into two. One which goes to one 400 ohm resistor, and the other pathway which goes down the other 400 resistor as well. Okay, and then there's the pathway that goes through the 25 ohm resistor. Okay, now whatever current I have here at this part, it must split somehow, maybe equally, into these two pathways. When these two pathways meet up again, like they do here, I must have the same current, because if you look at this circuit is essentially a series circuit. Whatever current I have at this point 1, I must have at this point 2, I must have a point 3, and I must have point 4. What happens here in this parallel section is what's different. Here the current must split somehow. But like we were talking about the mountain pass before, where if one particular path had high resistance, less current would go down it, and if one pathway had low resistance, more current would go down it. But in this case, the pathway is actually exactly the same. They're both 400 ohms. So in this case, you'd expect the current to split equally down both pathways. And this is exactly what happens. So we've already worked out that the current going through this particular pathway is 0.05 amps. Because this is the same resistor on this side as it is this is 400 ohms, this is 400 ohms as well. Therefore, you know this is 0.5 amps as well. Okay? They must have come from somewhere. It doesn't actually tell you in the diagram which side is positive or negative. Okay, but if we say, for example, that the current's moving in this direction, so it's going from here to there, then when the path joins again, I've got 0.05 coming here, I've got 0.05 coming here. I must therefore then have a combined total of 0.1 amps going through this 25 ohm resistor. That is 0.05 plus 0.05, both pathways coming together. If I had 10 people here, 10 people here, I'd have 10 plus 10, I'd have 20 people going down this pathway. Okay, so that's how we've done the second part of B. Okay, the question, if we reiterate the question said, calculate the current going through the 25 ohm resistor. This is how you do it. You know there's 0.05 going through the 400, you know there's 0.05 going through the other one as well. You just add them together, adding both of these together. Both pathways come together to form 0.1. And the same happens in the opposite direction. You know, the 0.1 splits. Okay? Got 0.1 here, 0.1 at 2. It splits. At 3 we've got 0.1, at 4 we've got 0.1. It's still a series circuit, but with a parallel part to it. Okay? So that's the 6b part 1, sorry, part 2. 6b part 3 then starts to talk about calculating the potential difference applied to terminals A and B. So they want you to work out the potential difference between A and B, okay, across the whole thing. Now we can redraw this. Again, don't worry about it being a vertical section. We can draw it horizontally if we want. What we have is a 25 ohm resistor here. We have a parallel section. Sorry about the wobble. I'm trying to stop it, but it's difficult. We've got a 400 ohm section, a 400 ohm section here, and this joins together, and this is A and this is B. It's the same thing. I've just packaged it in a different way. It's exactly the same thing. 25 ohms, 400 ohms, 400 ohms. Okay, that essentially, you can see, we can recognize that as a nice series circuit, but with a parallel section to it. I know that the total voltage across A and B, we can call it VT, V total, that must be split amongst each of these sections. I've got one section here, I'm going to call V1, if I had a voltmeter, and if I have a voltmeter here, across V2, I know that whatever voltage I have here must be split somehow, or shared. It's shared amongst the V2 and the V1. Both V1 and V2 combined together should give me the total voltage. Okay? Both V1 and V2 combined together give me the total voltage. Do we know what the voltage is across the 400 ohm resistor? We've already calculated this in the first part of the question. We've used I squared R, and we found out the resistance. We know the current going through this is 0.05. If the current going through is 0.05, then therefore voltage equals current times resistance. 0.05 times by 500 ohms, 400 ohms, sorry, gives us 0.05. Let's turn this on. 0.05 times 400 ohms gives us 20 volts. 20 volts. So I know already that there's 20 volts across this parallel section. Because this is a parallel section, there's 20 volts across this 400 ohm resistor, and there's 20 volts going across this resistor. Both resistors, because it's a parallel setup, this bit here, they both have 20 volts across them. But that's not the whole story. It's asking you for what's across A and B. Or if you look at this diagram, across A and B, we know there's 20 across here and here. Between this point and this point, there's 20. There must be some voltage that's shared across the 25 as well. How do we figure out what that is? Well, we know already what the current is going to the 25 ohm resistor. We just worked that in part B, the second part to part B, and that is we worked it out as being 0.1 amps. We know the resistance is 25, so you can V equals I times R. I can work out the voltage as being 0.1 times 25 equals 2.5 volts. There's 2.5 volts across this 225 ohm resistor. Okay? So using the current from before and using the resistance that's we've already been told, I know this is 2.5 volts across this 25 ohm resistor. Okay? So therefore, I know the V total is equals V1 plus V2. Okay, I know that whatever the total voltage is in the battery or whatever power supply here, that voltage is shared equally amongst each of the components. Okay, if there was another series resistor here, it would be shared amongst that one as well. Okay, but because this is parallel, there's not a separate voltage across this 400 and a separate one across this 400. They're both exactly the same because it's parallel. Okay, I know there's 20 volts across here, I know there's 2.5. Therefore, it must be 20 plus 2.5, which gives me 22.5 volts. 22.5 volts, and that's the answer, and that's how you work out the final part, 6b part 3. Okay, so again, looking at it vertically, I'd have 2.5 volts across here. Okay, and I've got 20 volts across here. It's the same thing, 20 plus 2.5. 20 plus 2.5 gives you 22.5. Remember, in a series circuit, the voltage is shared among each selective component, whether it's a series module or whether it's a parallel module. It doesn't matter. We could have a couple of parallel modules. They'd all share a certain amount of voltage, but you know the total voltage is going to be a combination of each individual unit because this is a series circuit. Okay, I know you're used to looking at a series circuit like this, but this, even in a vertical position, it's the same thing. All I've done is drawn this, but to one side, in a horizontal fashion. Okay? You've got to get used to looking at circuits in both ways and figuring out it's the same thing. Okay? Hope this helps. Email me if you still got any problems. Thank you. Bye.